Session with Prof. Fendley from the University of Oxford. We will talk about Baxterising using conserved currents.
Thanks for having me. I'm another physicist like Hubert, and I'm going to tell you another thing about connections between. All right. I'm going to tell you, like Hubert's talk, I'm going to tell you about relations between statistical mechanics and the topics that most of the people here study, conformal field theory, fusion categories, and all that. But I'm going to focus on although in some ways it's very closely related to what Hubert talked about, it's going to seem completely different because I'm going to focus on topological aspects of the story, which not the Virasoro part of the story. So there's an old story coming from the 80s that two-dimensional lattice models, particular types of lattice models, are conveniently described in terms of not-link invariants. And Vaughan, one of the organizers, who told me he was going to take a nap at lunchtime, which is clearly a fatal error here. But anyway, so Vaughan was one of the pioneers. In fact, there's an algebra that people call the Temperley-Lieb algebra that Vaughan actually independently rediscovered, but not everybody knows what Temperley and Lieb were doing when they discovered their algebra, although most people here have probably heard of the algebra, but they were doing statistical mechanics and showing that you could rewrite certain interesting statistical mechanical models in terms of their algebra that bears their name. And so and as I'll explain, that's the Temperley-Lieb algebra and other such algebras play an important part in knot invariants, if you didn't know that already, and I'll explain that. So there's a whole great story in the 80s, and I'll talk a little bit more about that as the talk goes on. But I think it's fair to say that at least in physics, that's mostly been forgotten, or was forgotten for a while. And certainly, I'd say in statistical mechanics, that's mostly forgotten. But what happened in physics in the last 10 or 15 years, and then you've heard bits in this conference as well about this, is there's a lot of excitement in trying to find models that exhibit interesting topological behavior so you can build a quantum computer for them. That's a whole interesting story. But one of the byproducts of that story is that it meant a lot of physicists now know something about knot invariants. And whereas most of that application has been to certain kinds of quantum physics and quantum information, what I want to do today, and one of the themes of my work in the recent years, is to apply that stuff to statistical mechanics, or revive this old story. And the moral, and why this is a good after lunch talk as everybody's settling into their nap time, is you can prove things by drawing pictures, which I like. So anyway, I've got words at the beginning, but then there's going to be lots of pictures. Okay, so let me give an example of this. Though this is not exactly what the talk is going to be about. This is some closely related work I did with Dave Austin, who's a grad student at Caltech, and Roger Mung, who's on the faculty at Pittsburgh. And we've got one paper out. There will definitely be another one by the end of the summer, and then there's many more in the queue. It's a whole epic thing. And it's so epic, I couldn't figure out how to talk about that, which is why I'm going to talk about something related. But I want to tell you about I want to advertise the story, and also we're going to use some of these results in the story I'm going to tell you. And so what we've done is show how to use fusion categories, which many people here know far more about than me, to find topological defects in lattice models, in large classes of lattice models, certain types, but large classes. Now, these include many integrable models and the kinds of models I'm going to talk about specifically later in the talk, but they also, if you stagger Boltzmann weights for the experts, you can get non-critical models and non-integrable models in this story. And if you know a Kramers-Wanier duality, this allows you to generalize that enormously to these things. And in fact, we can start to make contact between the lattice and the continuum, and that we can do exact calculations on the lattice. And for example, modular transformation. So a modular transformation is perfectly well defined in a lattice model, and we can define it exactly. So if you wish, if you're familiar with the story, the sectors of the CFT in the lattice model become wrapping various topological defects around cycles of the torus. And so we can then derive the modular transformations exactly on the lattice, and if you look at their eigenvalues, or in a more physical way of saying it, the momentum quantization conditions, you get exact dimensions of operators. So this now doesn't prove that if you take the continuum limit of these lattice models, you get a CFT, but it does prove that if there is a continuum limit of this lattice model described by a CFT, then you know dimensions of the operators in the CFT. So it's in the same spirit as a lot of results in SLE, whereas you can prove things rigorously. If there's a continuum, it has to be this. So I'm not going to prove any continuum limits, but for a physicist, that plus a few numerical checks is usually good enough for us to believe everything, and I'll leave it to you all to actually prove that you can take the limit like Vaughan was trying to do. Anyway, so the specific that I'm going to talk about, closely related to the previous slide, is how you can find conserved currents in lattice models. And one of the, so I'll be much more precise about what these things are, but one of the things this guides you towards solutions of the Yang-Baxter equation. And these things came up in some beautiful set of work pioneered by Smirnov and then John Carty, Stas Smirnov, by John Carty, did a lot of, I think, insight on top of that. And they named them, and for reasons I will explain, it's a bad name, discrete holomorphic operators. And I'll explain that what they really are has something to do with conserved currents. So in the title of my talk is a funny word that Vaughan invented, which is Baxterisation. And so we kind of come full circle now back to the 80s here and doing what we're doing is because when Vaughan invented the word Baxterize, what he meant was to take some knot invariant you have and or braid group representation or something topological, and you convert it into a solution of the Yang-Baxter equation. If you don't know precisely what that means, I'm going to explain precisely what that means. And the slight distinction is when you're in knot theory and all that, you don't have typically you don't have a key parameter in the lattice model, and it's the spectral parameter that Vaughan mentioned yesterday. So anyway, so that's the overview just for people who know something about lattice models. I'm going to talk about a variety of types of lattice models, and the main thing will be geometric models, but I'll emphasize, and I will throw in a few slides, that everything I say will apply to lots of spin models or height models. And also by taking a certain limit of the transfer matrix, this all applies to quantum Hamiltonians too. But just a quick comment. All right, so here's maybe the canonical model, and this model does have something to do with Temperley Lieb. Well, it's more or less why Temperley and Lieb, more or less the model they were studying, or at least a closely related model to the one they were studying. And so what this is now the degrees of freedom is StatMech model, so you're doing counting, so with some probability, so StatMech is, I don't know, combinatorics or probability. So in geometric model, the first kind of models I wrote in the previous slide. So the degrees of freedom are loops on the square lattice. So the dots are the dual square lattice, but these loops live on another square lattice. And it's called a completely packed loop model, and there's a completely packed. And so what that means is every edge of this lattice, this dual lattice to the one with the dots, is covered by some loops. So that's not very interesting, but the interesting thing comes is you don't let these things cross. So at every vertex of this lattice, they avoid, or in one of two ways. So they avoid vertically, so that's something like that, or they avoid horizontally, something like that. And now I assign a partition function, or if you wish, compute this object, which lets you compute all sorts of interesting probabilities. And the interesting bit is that we assign a weight d. D is a number. It's not the same d as either Arthur or Vaughan used yesterday. I think it's this d squared minus 1 was his d yesterday. But in any case, so it's d to the number of loops, and v is then some number that you weight every time you have a vertical avoidance, and h is some number that for each horizontal avoidance. And then the object in statistical mechanics is to compute this object. So let me rewrite this in a form that's, I mean, so far is just literally just a rewriting, but this is the form in which one would like to rewrite it to make contact with this much bigger story of tensor categories and that. So what happens is at every vertex of the lattice, so by every vertex I mean, again, every time I have this choice between avoiding horizontally or vertically, I just draw a dot. And then so the dot means this linear combination, and I assign a weight v to be the vertical avoidance plus that. So you should think now, this is a linear combination of this. And now I can just write the partition function in a more concise way. So what that means is you take each dot, you expand it out into the two choices you have at each vertex, and then I evaluate it, which just means well, you got these factors v and h, these numbers, these weights there, and you take these, you include those numbers for each vertical horizontal avoidance, but then the interesting bit, the interesting topological bit, is you take d to the number of loops, this number d. Now that's highly non-local because it's topological. You have to look at the whole system to see if a loop comes back and reaches itself again, so you know how to count loops. One of the interesting things going way back to temporally Lieb is for certain special values of this parameter d, you can actually turn this evaluation into something local. And I'll say a little bit more about that later on. Anyway, so that's a canonical model, and that's just rewriting. So it's just counting loops with these weights. So why? Well, one of many reasons that model is interesting is because it has a solution of the Yang-Baxter equation. So the Yang-Baxter equation is one of the mothers, maybe the mother of integrability. And so what it says is if weights in a model, Boltzmann weights, those weights I put in that partition function, satisfy a certain relation, then essentially the model is integrable. And integrability doesn't have, the precise definition of integrability is a little bit amorphous. But here there's a very precise definition. What it says is if it satisfies this equation, then when you set up a transfer matrix, you can define a transfer matrix, I should say, that commutes as a function of a certain parameter. And that's the parameter that doesn't appear in knot theory, but does appear in statistical mechanics. So in this slide, I wrote v as some function of some u and h as some function of u. So that's the parameter u. And what we now say is there's this Boltzmann weight, it's a function of some u. And then if the Boltzmann weight satisfies these relations, so you literally just multiply all that stuff out. Vaughn yesterday mentioned, so really what you need is these, u and u prime are independent. This has to be some function of them. I made a slight specialization to emphasize the fact that in most of the solutions that people understand of this thing, the third parameter, this one, can be written as the sum of the other two. And when you do that, you can interpret all these as angles. That's not always true, but it's usually true. I can explain when it's not true if people want later. Okay, so that's the Yang-Baxter equation, and that guarantees commuting transformations. Vaughn explained that yesterday, so I don't say any more. So now we literally just plug in our expression for this model. Okay, so v and h are just some functions, and you can scale out overall, so I'll define the ratio of the two, and then the overall constant doesn't matter. And then you crunch through with the key thing that if you have a closed loop, you give it a weight d. So that's why that d appears there. And that's what the Yang-Baxter equation is for this model I just wrote down. Just some nasty functional equation, which maybe some people can just inspect and get a solution. You can mess around with it. If you mess around with it long enough, you'll find the solution I'm about to write down, but there's the solution. If I write this Q, and this is the Q that appears in quantum groups, and then D is just this number there. So Q, for the interesting cases, is some root, well, for certain special cases, a root of unity. Then that W of U turns out to be that, if I didn't screw up my notation. Something like that, but I think I got it right. All right, so that gives you an integrable model. But, I mean, long ago, people noticed, well, that's awfully simple given how nasty this equation is. And moreover, for generic models, you try and do this and there's just no solution. Wildly over-constrained system. But in some cases, not only do you get solutions, you get very beautiful and simple solutions. Like, I think that one is right there. That's trigonometric if you parameterize. That's some sine of something over sine of something else. So if you, it's really nice. So anyway, so one solution to this story, I briefly mentioned, is quantum groups. I'm going to avoid that completely and tell you the connection with the other story I mentioned at the beginning, which is knot and link invariance. So this, for this audience, is probably utter and complete review, so I'll go through it really quickly. But it's important to satisfy notation, and there's one point that, one non-obvious point, maybe even to the experts, that I want to make at the end. So the story Vaughan did in the 80s was show how to define topological invariants from knot and links. You project them down onto the plane, so you get overcrossings and undercrossings. And then you do something that's exactly of the same spirit what I did with the Boltzmann weight. So I had that red dot, but what you do here is you take this overcrossing or undercrossing, and you place it again with a linear combination. And Q is some parameter, which of course will turn out to be the same parameter that I defined a few minutes ago. So it's not a coincidence. So I take this linear combination, and then you get a sum. So what we've done now is, if you wish, resolve each crossing into a linear combination of horizontal and vertical avoidances, and with this number Q in front of them. And if I then do the same thing, I replace each loop. So I evaluate this graph, I replace this loop. That, up to one important subtlety, gives you the Jones polynomial. And so that's the old story, and it just works out beautifully. And I wrote it in a fashion to emphasize that it's pretty similar to the stat mech I told you about before. So of course there. So let me just quickly show you why this works. So there's the Reidemeister moves. So of course there's ambiguity in how you project your three-dimensional knot or link down onto a plane. You can choose different planes. And so, of course, you might end up something where something crosses over and then crosses over again. Obviously, topologically, those two are the same. So if it's a topological invariant, you better get that. And sure enough, you plug in that linear combination that I wrote in the previous slide. Well, you get these four things for these two overcrossings. And, sorry, an overcrossing, undercrossing. And so then you get this linear combination. But remember, this gets this weight D, and D is precisely minus Q inverse. So those cancel, and you get that. So that one works. Now, where people often call the third Reidemeister move the Yang-Baxter equation, I don't like that, because I want to emphasize the Yang-Baxter equation has a parameter, and the third Reidemeister move, which is this one, doesn't. So this one, you can see, is topologically, you just drag the middle one kind of underneath, and you get that. So that's another topological invariant. The third Reidemeister move long predates Yang-Baxter anyway. So. But where the connection comes up, obviously the picture looks very similar. That's why people often call it the Yang-Baxter equation. But what I think it's better thought of is one can often obtain solutions to this by taking a certain limit of this parameter u. And in the usual conventions, the ones I gave before, you take this to I infinity. And then you get solutions. So from Yang-Baxter, you get the third Reidemeister move. So again, that's the old story. Now here's the bit that's again, known to the experts, but maybe not everybody. There's one other Reidemeister move. If something just doubles over itself, it has to be topologically equivalent to itself. But I'll tie my shoe and say the word. But the point is, if you plug in our relation to that one, it doesn't quite work. But it doesn't quite work in an interesting way. So you plug that in, you get that linear combination. You get rid of the loop by just replacing with the value d. So some bits cancel, but you still get left with this. And this is some phase in most of the examples people are interested in. So it's not quite. Now there's a way to get out of it. This is the subtlety I mentioned before. What you have to do, since this audience knows this, you can take off your belt and show people. But the point is you make each knot into a ribbon, and then where that sort of looping around corresponds to a twist in the ribbon. It's called framing the knot. And you can keep track of these twists, and you can basically get rid of this factor minus q to the 3/2. And so that's the story. But that bit is going to come back later on. So in fact, when we're doing this is good. We want this. So as opposed to sort of an annoyance if you're interested in a knot invariant and you have to get rid of it, we want this. And I'll explain that as we go on. Okay, so. All right, so now I wanted to mention these other kinds of models. The first model I wrote down was a geometric model. I'm going to say this very quickly, but since many people have heard of models like the Ising model, I want to say the Ising model can be written in this form. Actually, many models, the Potts models, that's actually what Temperley and Lieb were studying when they started out doing this. Parafermions we heard about, and I'll mumble a little bit more later on. more elaborate ones often called generalizations of Baxter-Forrester models. Lots of models. These are the local models. All the models I have on this in the black here are all locally defined models. But it turns out through some magic that it follows from the kinds of things I'm going to tell you about. I'm not going to explain how this works in detail. You can write this in this form. And so if you just look more abstractly what this form is, this weight d is the topological weights because it depends on the number of loops. So I'll call that a topological weight. This one you can measure locally, the v or h, whether there's horizontal or vertical avoidances. But all these models can be written in that form. And this, in the math world, is called shadow world, or in this context of categories. And so again, let me just flash a slide for those of you who like these things. So what happens is you define a dual square lattice, and the heights live on that. And then, again, if you like the Ising model, it turns out for technical reasons, you actually make the Ising model live on half the sites. But if people want me to explain that, I will. But in case people want to see where Ising comes from. And these models, again, Baxter has studied in many forms a long time ago. And let me just write out now what the Yang-Baxter equation looks like for these models. So what we do is, so these are our loops or whatever geometric objects we're studying. And then the heights will live on the dual lattice, or I should say the faces of the lattice made by the loops. And so that's where all the heights will live. So they may take on plus and minus values like in Ising. They may take on other ones in other models. And if you wish, so then what these models typically have is interactions for around 4 points. So I draw that. So that Baxter named these interaction round a face, and so these are the models. And again, you can think of this as the u and the u prime in the solutions. Many of the solutions can be interpreted as angles. So I want to mention that because the story I'm going to tell you makes computing in these models really, really easy. So I wanted to make sure that it was clear that we did. All right, so now back to the main story. So what I said is at the beginning I was going to Baxterize these things. So I was going to relate a fusion category to solutions of the Yang-Baxter equation. And so now the sort of new innovation of this talk is sort of starting now. Everything I've said so far I think is pretty ancient. This bit is just introducing my bit, but let me tell you another story that's probably not known to most people in this audience, and it's a story called discrete holomorphicity. This is the thing I mentioned at the beginning that Smirnov and Carty have thought a lot about, and so let me say more precisely what they do. So they take some lattice model. Actually, they pick some lattice model. They determine which lattice model, and then they say, well, let's now see if we can define an operator. So expectation value is something like measuring whether a spin is up. This is a more complicated object, but they pick some operator in that model. And then they say, can we find a certain special operator that satisfies a lattice Cauchy-Riemann equation? And so what they mean is they got operators on, say, 4 points, say ding, 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 ding. And so if I now, these are my lattice points, and then I just do the discrete version of a contour integral, and then demand it vanishes. So it's saying, I'm going to look for objects like this. Now, why Smirnov thought to look for things like this is because there's some ancient stuff going back, to the 20s in physics. It's called the Jordan-Wigner transformation. And then defining these operators went to Kadanoff and Seva in circa 1970. So ancient stuff, again, parafermions come from these same ideas. And people knew they had these special properties. So Smirnov thought, let's look at these operators. And the reason why he wanted to do it is because if he can prove now that they satisfy these equations on the lattice, well, then maybe he can prove that really prove there exists a limit. Because if it satisfies a lattice version of analyticity, well, maybe I can bound things properly and show that when I take the continuum limit, it becomes a holomorphic operator, and these operators are crucial to conformal field theory. And he succeeded for the Ising model. So it's got him a Fields Medal, so a very successful program to do that. So that was the idea to look at things. So let me draw schematically a picture. So pictures you'll see in these papers. So U is, so this again is the same Boltzmann weight I drew before, like in the completely packed loop model. But then we define some other operators. So this is schematic. I'm going to talk about how to define this precisely. And then I do things like this. So again, I'll have to define the overcrossing and all that. But schematically, this is just dz1 is just the spatial difference there. And so what he's saying, I want to define operators so that in a given lattice model, this equation is satisfied. And of course, if he hadn't found them, I wouldn't be telling you this, but in many examples there. But there's a catch, right? So if you look at these equations, they found lots of things solving this, but it's not good enough to prove holomorphicity. And because it's only so if it just satisfies what I wrote here, it only satisfies half the lattice Cauchy-Riemann equations. And the point is that, so if these degrees of freedom, this operator is defined on the edges of, say, the square lattice, the models they were typically looking at. So it's defined on every edge, but I only have one of these equalities for each side of the lattice. So there's twice as many edges as sites on the square lattice. So you only have half the equations, and there's no such thing as a half holomorphic function. If there is, I don't know what it means. And anyway, so it's halfway there. It's really interesting, but it's only halfway there. So for Ising, the case Smirnov used this approach to work, there's more equations. Get another set of equations. So he has as many equations as unknowns, and he can then prove stuff. It's constrained. But half is not useful for the intended purpose, and that's why I said at the beginning, calling this discrete holomorphic is really, well, for most examples is not right. And even if you believed in miracles, I think, we want physicists, actually, yeah, mathematicians you guys are supposed to be careful physicists. We like to believe in miracles, but we actually checked in the three-state Potts model that the parafermionic operator there, you just define it in a very standard way. Been known for decades how to do that there, and you can show it beautifully satisfies that relation, but it doesn't turn it into a holomorphic operator, and we checked it in two ways. In fact, we checked it numerically, of course, like good physicists, but on the other hand, we actually also checked it in the conformal field theory. Fiteyev and Zamolodchikov actually missed a term in their operator product expansion. So it's just actually, there's another term there that's not holomorphic, and so it's not there. Anyway, but anyway, let's proceed onward, and there's a reason to proceed onward. So it didn't work for its original purpose, but I'm going to explain how to repurpose it. But it was very curious. So Smirnov did this for Ising, and then he found some generalizations. Carty found lots of generalizations. But then Carty also, and his collaborators, also reversed the order of logic in an interesting way. Instead of saying, well, here's my favorite lattice model, and I'm going to look for these operators, he says, well, I'm going to pick sort of the type of lattice model. But, so say I'm going to talk about a completely packed loop model. But I won't specify the exact Boltzmann weights. And then they say, can I find Boltzmann weights such that this condition is satisfied? So instead of picking the Boltzmann weights and looking for a conserved current, they go the other way around. So schematically, what Smirnov said is, here's my favorite integrable model, and then I'm going to look for an operator. I'm going to define this vertex here so that this thing is satisfied. Carty said, let's assume that this is true. Can I find the red dots? Can I find the Boltzmann weights? And what the interesting and important thing that Carty and collaborators found was that if this were true, if you could find this, if you could specify the Boltzmann weights, well, then these Boltzmann weights always turned out to be solutions of the Yang-Baxter equation. That's not a proof, but every single case they worked out, it's also a solution. So it's not a proof of Baxterization, but it says, it's starting on there. It's saying, here we're defining something, we satisfy a simpler relation, we get a solution of the Yang-Baxter equation. So it's starting again there too.
Crossings between the dotted red ones and the blue ones, are they supposed to be some other local?
Yeah, so I'm going to talk about how to define that. momentarily. So I drew it as a braid, so you can think of it as a braid for now. We don't, doesn't have to be, but we can, if we have a category. So far I haven't brought the category, which I'm going to do soon. Not quite yet. Okay, so I'm going to discuss, so the last bit of the talk will be actually how to solve that equation using tensor categories. I just want to say at least an interpretation now. So they invented these objects. They work for icing, but they don't have their original purpose there, but they're very interesting. So what do they mean? So I gave a talk, ancestor of this talk, a long time ago now, 2012 in Berkeley. And Denis Bernard was in the audience, and I drew exactly that picture, the one on top here there. And he got this disgusted look on his face and said, "What are you talking about? This has nothing to do with holomorphicity. This is just a conserved current relation." And so he pointed me to this paper that he and Felder wrote in '91, if you can read it, but '91. And there's their relation. It's exactly the same as the relation I wrote down with the bold move as they move two of them to the other side. It's okay. And if you think of the DZs there, it's just changing the sign on the DZs. So in a way, this is just as natural. So this is literally in their paper, equation 210. It's exactly the same equation. And they showed using quantum groups how, at least in the SL2 case, how to construct such operators. So in fact, they invented these operators well before Smirnov and Carty did. And so that's the Denis relation again. And so now, why did Denis call them conserved currents? Well, if you think of this as sort of time is going this way, this is kind of an in state. It goes, the transfer matrix acts there, and then that's an out state. So let me draw in my pictures. So if now I take this linear combination of all the operators on the vertical link, so Bing plus all along, well, then I can use this relation to show that that's equal to this thing. Because then what happens is the ones on the horizontal links all cancel. Boundary conditions are important, but let me avoid them today. So up to boundary conditions, the following equations are true. It commutes with the transfer matrix. You take that linear combination of these objects, it commutes with the transfer matrix, and this is what physicists always call conserved currents. This is sort of local currents conservation relation. It looks like a divergence-free condition, and that's what it is. So, and if you go to the Hamiltonian limit of the transfer matrix, it commutes with that too. In physics, we often call these zero modes. A lot of my life in recent years has been spent studying certain kinds of zero modes. Not this, but related ones. All right, so that's what they are. And so now that they're a conserved current, now it's not shocking why you get solutions to Yang-Baxter, because you're showing that the transfer matrix of the model has a really non-trivial conservation law, commutes with this psi. And well, that doesn't guarantee integrability. Of course, where there's smoke, there's fire. So if you're finding interesting stuff going on, well, then maybe it's not so surprising that the full model is integrable. So it's an easier way to get at integrable models. And it's remarkable. I mean, you can take models where you have to tune the Boltzmann weights to get it to be integrable, and demanding this precisely tunes them to the integrable point. So in the temporally Lieb case I showed you, it's integrable for all V and H. But when you come with more complicated examples, you get multiple things, and they all have to be tuned to be integrable. And demanding this gets it all. So it's really a non-trivial statement. So that's the meaning. So just rename the discrete holomorphic operators conserved currents. That's all we need to do. All right, so now for the last third of the talk, what I'll do is explain how tensor categories, stuff that you all know, or at least many of you know, give you a really nice way to find these. So the way Smirnov and Carty done is just kind of ad hoc. You look at a model, you think they're smart, you work hard and crunch it out, and you can do it. And because the equation is linear, this is possible. But I want to find a general way to do it, and so that's what the tensor category gives you. So anyway, so what you do is, so that trivalent vertex I drew in the schematic pictures, and that string coming off of it, this hands us exactly the tools we need to define those in lots and lots of lattice models. And again, in all the cases I checked, which is now even more than what Smirnov and Carty found, it always again solves Yang-Baxter. So it's good. I should say also, I'll mention at the very end something that even goes a little bit beyond the old story. All right, so that's now the setup. So we're going to use, so those pictures now we can define precisely in these lattice models. So the first thing actually, before, the vertex is actually easier, but the string is the hard part, but it's really important. So anyway, so here's our lattice model. Here's my completely packed loop model. I'm going to define something there. Let's ignore that for a second. But what I want now, there'll be some string there. And if you know about fermions and the Ising model, this is, again, physics told us a long, long time ago what this string has to be to have nice properties. Excuse me. And we want to generalize this. And the general language for this is we want this object to be a topological defect, which I'll define precisely in a second. But let me just say the idea is that then this expectation value will be independent of the local deformations of the path of this string. So the string definitely matters, but I can move the string around, it doesn't matter. So let me explain what a topological defect. So this is the story that I've been working on with Dave Ossen and Roger Mung in great depth, and these guys have gone to town on this. So here's, all right, so now let's draw real pictures. So here's my square lattice, although what I'm about to say works on any lattice of rhombi. But anyway, so this is now the string. So imagine it's connected to something at the end. We'll ignore that. So this is the string, which I'm calling now a topological defect. And so here's how I define the topological defect. Okay, along that path, so I just cut the lattice momentarily. We'll glue it back in a second, but I cut the lattice along the path of the string. And then I draw these little quadrilaterals here. And what the quadrilaterals are, you should think of as defect weights. So just like I drew at the very beginning, those dots, which I've left off now, we have these dots there to tell you the Boltzmann weights depending on the heights or the loops or whatever degrees of freedom you've got. Well, now I'm going to assign weights to this defect. But of course, I have to choose the weights so that it doesn't matter how I draw the string, or at least up local deformations of the string. And so what's in our papers, so we wrote one a year ago, although that focuses on the Ising model. We tried to write everything so it was obvious in general, and then the one that will be done by the end of the summer will explain how for any fusion category, if you take the Drinfeld center, it allows you to define this object such that it satisfies this property. So in other words, it defines these weights, and I wrote this in the height picture. So these are the things living on the sites of the lattice. These heights are spins. And it satisfies this equation. And for people who know what the Drinfeld center is, this is just a rewriting of that relation. But the point is we can make a precise dictionary between all the things that come up in these categories and the things we need in a StatMech model.
But what about the vertices that involve 3 greens and 2 blacks?
3 greens. Yeah, that works too. Yeah, I just drew the one, but yeah. No, everything works. Yeah, no, it's absolutely. No, we checked it all. And what's also, what's also nice is there's all these annoying signs to begin with, but it turns out if you write things out carefully enough, all of these phases and all this nasty stuff all cancel. It really works out beautifully. There's a formula literally just in terms of the F symbols for this. So, so we know how to do that. So that work explains how to do this in enormous generality. In fact, so enormous we're not even sure how general it is yet. I'll maybe babble about that at the end. So now we need this one thing. So this was the bug. Well, what in the not polynomial is a bug, not a feature, but here it's a feature. The fact that when these things twist around, when these things twist around, well, then you pick up this phase. And this is exactly what you want for these holomorphic operators. Probably anyone who knows CFT here knows if you twist an operator in a CFT by 2 pi, you pick up a phase. Well, on the lattice, if you define this operator appropriately, you get the same property. And so the way you do that is to pick your category. So now I haven't been labeling lines, but the general picture, you label all the lines with objects in the category. We can say simple objects. And then you understand fusion in the category, and for the physicists in the audience, this would be how a combination of anyons braids, but you just define a fusion algebra. In the mathematical case, this is underline the fusion category, where this object, tensor with that object, gives you some linear combination of other objects. This is the object that appears in the Verlinde formulas. Again, most of you probably know. But I'm going to draw it pictorially like this. And I'll give you the, explicitly, I'll flash some formulas for the completely packed loop example I get. And in the category, so now I have to go to, for this to make sense, I have to go to a braided category. I actually don't think this is necessary, but I haven't shown it yet, so I'm going to draw it in terms of braids, because it's easier to draw anyway, and that's all that I've demonstrated too. So then you can define overcrossings and undercrossings, but the point is you can get rid of them by untwisting them and picking up these phases. So associated with each one of these objects is a number h sub a, and then you define this. But the point is the fusion, or so the braided tensor category hands you all of this stuff. So I don't have to do any work. And in particular, I get this property that I want for the operators. All right, so now let me try and schematically illustrate how this works for the loops. So I was saying everything's defined in general, any fusion, any braided category, I can define these objects. Like I say, I think you can do it for any fusion category, but I can definitely do it for any braided category. Oops. And so anyway, back to the loops. Remember, this is just a reminder. This is what the loop model is. We draw a bunch of loops on every link of some lattice, take the partition function sum over all the loops with a weight d per loop, and then these horizontal and vertical weights. But now I'm going to define the 2-point function of conserved current. Sorry, I called them psi here. I called them O before, but now I'm calling them psi. So they're located at 2 points, just write in complex coordinates, z and w. And this is definition. So now what I'm going to do is modify the partition function by the following. So the local weights stay exactly the same as before. But what I do is I draw this picture and I connect these two by a string. I've already shown that it doesn't matter the path of the string, but it does affect the total answer that you have a string. And then I use the rules of the braided category to evaluate this graph, which means turns this graph into a number. So again, those of you who know that story know how to do this. Those of you who don't, it's just a set of rules that turn a graph into a number. And now I've drawn a new graph where I glue that one on. I've defined the vertex, and I've defined a way of turning, the category defines a way of turning that graph into a number. So it's the loops plus the string terminated there. And for this example, the rule is really easy. It just says if two things are on the same loop, you get 1, and if they're not on the same loop, you get 0. So that's all. So there's no barbells, if you wish. The string doesn't connect two loops. That's the rule. That's it. Up to this twisting, but just whether you get 1 or 0, but then you get these phases if the thing twists. That's all.
So what about the red ones going over the blue ones?
The red one going over the blue ones. Well, so I just think of this as some so like I say, so the red one goes over the blue ones, but then if it's going over the blue ones, but the rule is if it connects the same loop, I get 1. I can just then forget the red one. If they connect two different loops, I get 0. That's all. And then forget it. So in generality, of course, it's much more complicated than that. In this case, it's easy. And for those of you who know about this thing, this is just the fact that spin 1 is orthogonal to spin 0. Okay, so that now so the fusion category, not only the braided category, I just keep saying fusion category because I'm used to the default. The braided category not only gives you the rules to define these objects, it gives you the tools to show that it satisfies the current conservation relation, the quote discrete holomorphicity relation, but we've renamed it now. Okay, so we've defined this, but moreover, we can now use the manipulation, we can do manipulations in the category to make it much easier to find solutions, and again, in great generality, and in particular, get it to work for height models. So you can do this by brute force, like Smirnov and Carty did for various geometric models, but the spin models is essentially impossible. So I'm going to just blast through this so apologies to those of you who haven't seen this before, but I think since a fair number of you have, I can just say this quickly. But just to say, so what happens is what the category gives you these rules that are akin to tensoring representation. So this fusion I talked about before, when it's A times B, or A tensor product B gives you C summing over C's with those non-negative integers. This is akin to tensoring representations of SL2. And the key fact that I use a lot is the fact that in this particular example, so for the completely packed loops, there's basically two ways to tensor 4 spin-halves into spin 0. So that's for the physicists in the audience. But the point is, what the category gives you are all these rules that preserve topological invariance. And so in particular, what it lets you do is define this the red line, the string in my operator, can be defined topologically as this. So all this is understood as the evaluation. So in other words, if I evaluate this graph, it's equivalent to plugging in these combinations and then evaluating each and taking the appropriate linear combination with this coefficient. And then this one's like that. And the fusion category hands you all these consistent rules, and that's the magic of it. So it makes these calculations so easy. You just go through the rules. And so, for example, let me just illustrate one of the rules. So remember, I said the reason why in the completely packed loop case that red string connecting two loops has to vanish if it's not the same loop is the following. Well, I rewrite this as that linear combination, which is that minus that, but then with the rule that a closed loop gets D, well, that cancels the 1 over D, and that's 0. So that's all it is. And the point is the category gives you this enormous set of models where you have these consistent sorts of rules, and it gives you these idempotents or projectors that allows you to do stuff like this. It also allows you to do change of bases like this. So anytime, so this is why in the completely packed loop case, I can always write it as this way or this way, or I can write it in terms of this. So there's 4 graphs I have here, if you see, but just like there's only two ways of putting 4 spin-halves to get a singlet, there's only 2 ways to do it, and so there must be some linear combination, and the coefficients are called F symbols, and they do that. So again, let me just flash. You can then get the braid matrix. Oops. You get the braid matrix from doing this kind of stuff. But then what you can do is instead, you can take the Boltzmann weights of the model, and instead of writing them in terms of the overcrossing, the vertical avoidance and the horizontal avoidance, I can rewrite them as that using these rules. And the key thing I keep emphasizing, you can rewrite them, but it gives you the same topological invariant. So anyway, so here's the crucial bit. So now the point is I can take each of this is one of the 4 terms in my conserved current relation, and I can write it as a linear combination of 3 different objects. And I can do this for all 4 by using these manipulations. Let me go back to the conserved current relation, that one. So I can do this so that was for this one, but I can do the same thing for all of them. And I can reduce those 4 graphs into 3 graphs in this particular example. Now, there's still a miracle here. So I have to then take the linear combination of all 4 of these, and I get then 3 relations. And you have to check, well, do you have a solution or not? So again, I still have a miracle at the end. I mean, I've got 3 equations, 1 unknown, but that's better than Yang-Baxter, which is many, many equations and a few unknowns. So. Anyway, and so again, of course, for this example, you get the same thing I wrote down a long time ago. And what's a remarkable thing is the shape of this rhombus here turns out is related to the angle U, which is not particularly, well, it's a well-known but not particularly well understood fact. All right, good. So let me just kind of give a sort of long wind-up here and just sort of say where I think this is going. So you can now do this for many examples, not just the, I mean, and already Cardy and collaborators and successors worked out many examples. But once you write down a category, now it's just a matter of writing the category. And like for the experts, you know, the example I gave, I wrote a simple object on each link, but you can take compound objects. That's how you get models that are called dilute models and so forth. One example I worked out, it works out easily, much easier than these really difficult solutions people made a long time ago for the Berman, Wenzel, Murakami algebras. And something I again want to emphasize again, this works for height models, which is impossible. You would have to be, the heights, if you remember, live sort of on the dual lattice, or I should say on the faces of the lattice. So it would be these horrible relations. If you try and write this down, even for kind of the simplest model beyond icing, which people in my world like to call the Fibonacci model or the golden chain, in the old days it was called the hard hexagon model. You got 11, I did this by hand just to convince myself that this was all true. You would get 11 equations, and they're all nasty equations. And I checked, I thought they would simplify, but they're all distinct equations. But you can just check that the simple solution I wrote down before solves all 11 equations. If you're interested in this, finding these conserved currents, you have to use the category. There's no way you could do this by brute force. There's no way you could do this using quantum groups. It's way too hard. So one thing is really interesting. So the models that you get by this way have always turned out to be critical for various reasons. And the solutions of Yang-Baxter are called trigonometric type solutions, like the one I wrote down. And that's why in the continuum limit, these have something to do with conformal field theory. But there's lots and lots of integrable models out there, not just critical ones. And so far, everything I told you doesn't work for those. And that's not surprising. The same thing in the quantum group language. You have to go to affine quantum groups and other even more difficult objects to deal with in that case. So it's an open problem elsewhere. But when you start to look for these operators, so now I'll go to the Hamiltonian limit, and instead of looking for an operator that commutes with the Hamiltonian, I'll look for an operator that, well, commutes, gives you the function back to itself. So physicists would call this a raising operator or lowering operator. So you commute with the Hamiltonian, you get the same operator back. I wrote it as delta E. This would shift the spectrum. So in icing, you can easily find these things, and that's why icing is solvable. But the very curious thing I found, and I'm still somewhat baffled as to why, but it works, if you take this very funny integrable chiral Potts model and demand to satisfy this condition, you can find this operator. And moreover, the only time you get a solution, this is precisely when it's integrable, which is not an obvious case at all. The way this was done was this incredibly circuitous route. So I mentioned before briefly that not always do solutions of the Yang-Baxter equation obey what they call the difference property, the fact that you can interpret these angles. Well, these chiral Potts models are examples of that. There is a solution of the Yang-Baxter equation, like I wrote down, but not where the third spectral parameter is just the sum of the other two. And, but nonetheless, this still works here. So I don't know why, but it does, and it's by far the simplest way of understanding why, at least, what's special about these points without having to go through the full-blown integrability allowance. Okay, so yeah, just a few things. So I put in a plug for some beautiful work by Vincent Pasquier that I've been obsessed with for now 30 years since he did it. But one thing to remind, so you can define now, so the operators I've been describing, even though they may not be holomorphic. So sorry, you take these operators and now go to the conformal limit. They don't give you a holomorphic operator, but they do give you a chiral operator. And so Vincent Pasquier had some beautiful insights that I still don't understand a long time ago. But one of the things that I wanted to emphasize this on is Vincent found the Verlinde formula before Verlinde did. I mean, he even called them N's and S's. Now, as a specific example and he was thinking about lattice models, but it is you look at the formula, it is exactly the Verlinde formula, and everything in the formula means exactly what Verlinde meant. But he was talking about these lattice models and thinking about these operators in lattice models. So that's still unexplained, though I think maybe we know a little bit more now about it now. I emphasize, so there's lots and lots of these models. So now, is there a whole zoo? Anytime I write down one of these things, there's lots of different labels. I mean, I don't know how big. There's lots of solutions to these equations, but I don't know how big. And in fact, I kept saying, I'm not sure you need braiding. Certainly for the topological defect story that I've done with Asen and Meng, you don't need the full braiding. The Grinfeld Center basically hands you all the braiding that you need. So does this work for Haugrup? Can you define some integrable lattice model based on Haugrup or half E6 or whatever your favorite non-braided tensor category is? All right, and so then just a few more speculative ones. Again, maybe you can use this to go back to Smirnov's program. Maybe, and certainly not all of these are going to be holomorphic operators, but maybe there's some other examples. And so SLE is a story that connected to this. But one of the most beautiful things in lattice models was a paper Hubert wrote with Vincent Pasquier, again, a long time ago, late 80s. And it really caused this enormous amount of effort in the StatMech community. Still goes on, although diminished, trying to apply quantum groups to lattice models. And of course, lots was learned. But the problem is the representation theory of quantum groups is beautiful but difficult. And maybe one of the morals I extract, at least from this, is maybe we should forget that beautiful paper and try a different way. And I think fusion categories are the right way. And of course, maybe this will get to the question, why are integrable models integrable? Anyway, thanks.
Nice talk.
So why haven't you done the Haugrup? Sitting there, forward and down? You've got all these
Because to see that it works, I need the numbers and all that. Yeah, no, I know, it just worked. Yeah. We haven't even done half E6, and we have it. Yeah, no excuse other than life is busy. That's all. No excuse. Yeah, it should be done. One of you can do it. I won't complain if one of you does it. Yeah.
When you define the conserved current by taking the sum over all things of these operators with a tail on the left, you said that it doesn't really commute because there's some boundary terms.
Well, you can often find boundary conditions that make it commute, I should say.
Oh, I see.
So it's subtle. If you're familiar with the old thing in the Ising model, this is the same thing when you turn the Ising model into free fermions. You have to divide things into sectors. So to be precise, you have to pick various sectors, and then you can do it within each sector and things like that. So it's a little bit subtle. Yeah. But if your motivation is just, of course, I want an integrable model, who cares what happens? But yeah, that's fascinating, and that then ties into this modular invariance stuff we did at the end, because what it kind of says is what you need at the edge is a topological defect, and then the string that goes in will glue into the topological defect. So, but that may not commute, but then that'll tell you, it'll relate different, but it'll be sort of psi will relate different boundary conditions. So it's not quite commuting, but it changes one sector to another. Yeah, so that's the more, that's
so
a much.
It's the best you can do to generalize the Jordan-Wigner transformation.
Yeah. Yeah. Yeah, right. No, so this does generalize Jordan-Wigner, but of course it's a more complicated one, so the boundary, there it's just a spin flip, so that's easy to deal with. There you just twist the boundary conditions. That's not how to do it. Yeah, but it can be done. It's nasty. Yeah.
About quantum groups, I have a question.
Yeah, that's right. No, I was hoping to provoke you with that.
So the comment is with Pasquier, we found this modular transformation on the lattice using quantum groups. I think actually
so there should be the same.
It was useful for this, at least at the time. But the quantum group generator is also just a zero mode.
Yeah.
Which is something that commutes with H. In fact, I thought in your construction what you were doing was building the quantum group.
Yeah, I think so. I think. Well, it's what Denis. I think it's yeah, it's what Denis did. I mean, that's exactly what Denis was basically doing. He was doing it. I should say he was doing it. Well, sort of in field theory and everything at the same time. He was more just doing the quantum group language. But I don't know if anyone ever did. You could take what the formal construction of theirs and then just sort of
But your
write it.
zero modes, what kind of algebraic relation do they satisfy in general?
No, that we don't know. No, that we don't. I mean, I know in some. So in the parafermion cases and all that, I know. In the general one, I do not. But I mean, in principle, you could derive. I mean, everything follows from these pictures. But I don't have a nice algebra. Meaning, everything is defined topologically. You can do these manipulations. So there's all the techniques are known to answer that question, but we haven't done it. Yeah. That's going to be hard in general, but some simple cases should probably be available. Or maybe.
Any further question? Okay, we take 5 minutes break and thank the speaker.
Okay. Thank you.